morning to everyone. I'm KODEESWARI, Assistant Professor in ECE Department at Konge Engineering College. Today, I will be presenting an overview of IEEE 802.11 MAC protocol, which plays a crucial role in wireless LAN communication. The focus of this presentation will be on understanding the MAC layer task, coordination function, and key mechanisms like DCF, backoff, RTS-CTS, and EAFS. The IEEE 802.11 MAC layer is responsible for controlling how devices access the shared wireless medium. The main task of the MAC layer includes medium access control, which decides when a device can transmit data without collision. And the second one is roaming, which allows the users to move seamlessly between the access points. And third one is authentication, which verifies the identity of the devices to ensure the secure communication. For example, in our college campus, if we are using the college internet through Wi-Fi, before entering into any website, first we have to log in with our username and password to verify our authenticity. This process is called authentication, which is used to ensure the secure communication. And the last one is power conservation, putting the devices into sleep mode when it is ideal to save the energy. So there are two main coordination functions we are using in the MAC protocol. The first one is DCF and the second one is PCF. The DCF stands for Distributed Coordination Function, which works based on CSMA-CA protocol. And it is suitable for distributed and contention based access. It is a mandatory method which is used in IEEE 802.11 MAC protocol. Simply, if we want to say, it is like the devices which are all having data to transmit to the receiver have to content to access the channel. Which one is in the contention will be allowed to transmit the data. So it is called distributed coordination function. And the next one is point coordination function, which provides a centralized contention free access method managed by the access point. In this method, access point will give a chance to transmit the packet by the device in sequence manner. So when the turn for that particular device is coming, at that particular turn they can be able to transmit data. There will not be any contention. It will be a centralized one which is controlled by the access point. Next, we will discuss in detail about distributed coordination function. So DCF is the fundamental access method of IEEE 802.11. It is based on the principle of carrier sense multiple access with collision avoidance. It uses FIFOQ for transmission. A station first checks whether the channel is ideal. If busy, it defers its transmission. A random backup mechanism is applied to avoid the repeated collisions. DCF uses a timing parameter called DCF interframe space, which is shortly called as DIFS, to prioritize the transmissions. In short, the DCF ensures fairness and reduces collisions by allowing the stations to wait randomly before transmitting. Here I have given the detailed view of DCF access mechanism. In the step 1, as I shown here, a device which is called as the source performs the carrier sensing and check if the channel is free or not. If the channel is free for a certain period, that is DIFS, it goes to steps 2. In the step 2, the source device send a RTS to the destination device. In step 3, all the other devices which are all hearing this RTS update their network allocation vector based on duration information in the RTS, so that they will not try to channel acquisition until the communication between the source and destination is done. And in the step 4, the destination device send a CTS to the source device after a waiting period of SIFS. And once the source device receives the CTS from the destination device, uh, and other network devices which are all present in the network will differs its transmission by using CTS message also. And then in a sixth step, after a short period which is called as SIFS, the source device sent data to the destination device. After receiving the data from the source device, the destination device will wait for the SIFS period, then it will send the acknowledgement to the source device. In step 8, after the completion of one data transmission cycle, all the devices, including the source and destination, should take another short break called DIFS. And in the last step, then every device will pass for a certain back off time for this is back off period is determined randomly for the devices. Then for the next transmission, each and every device will content to access the channel. This is how the DCF is working when we are transmitting a data from a transmitter to the receiver. Here we see how the contention window works in back off. So as I said earlier, uh, if a channel is trying to transmit in all the remaining devices in the network allocation vector will be set, and it will not try to access the channel in that particular period of time. So each station randomly selects a random back off value within the contention window. The contention window minimum size and maximum size will be decided based on the number of users in the network. If a transmission fails due to collision, the contention window size will doubles, which reduces the probability of another collision. Once the transmission is successful, the CW is reset to its minimum value. The formula for calculating contention window size is twice the contention window size plus 1 minus 1. This is an adaptive mechanism which allows the network to handle the congestion more efficiently. So each and every time when the collision is occurring, the contention window size will be doubled approximately when comparing to the previous contention window size. So next, let me discuss about the RTS and CTS mechanism used in the DCF coordination function. We all know that. So how it is avoiding the hidden station problem? That's what we are going to discuss in this slide. One major challenge in the wireless LAN is the hidden station problem, where two stations cannot hear each other like A and B. In the figure, you can able to see the A's coverage area is represented in the green lines, and B coverage area is represented in the yellow dotted lines, and C's coverage area is given in the blue dotted lines. So from this diagram, we can able to understand A and B are in the communication range. At the same time, C and B are also in the communication range. But the A and C are not able to hear each other. So in this situation, the hidden station problem will occur. So to solve this, IEEE 802.11 uses the RTS CTS handshake, which stands for request to send and clear to send. The sender first sends a request to send frame. Means that, for example, we will consider here A is the sender. So first it will send a request to sender frame. The receiver replies with the CTS frame. Once the CTS is received, the sender transmits its data and others will defer its transmission. The diagram here shows that station A wants to send the data to station B, But there is also a hidden station C, which cannot sense A's transmission directly. First, A sends a request to send frame to the station B. Station B replies with the clear to send. Station B here is replying with the clear to send frame. The CTS is also heard by the station C. Once the station C hears the CTS, it knows the medium is reserved and it stays silent. Now the station A transmits the data safely to station B, and finally B responds with the acknowledgement. This way, hidden stations are alerted through CTS and collisions are avoided. And in the last case, let me discuss about the extended interframe spacing. Already we have discussed about SIFS and DIFS. SIFS stands for short interframe spacing and DIFS stands for distributed interframe coordination function interframe spacing. When comparing these two, SIF is very shorter when comparing to DIFS, which is given for the acknowledgement. And if we want to transmit any packets from one station to another station, the DIFS period is used. Here, let me discuss about the extended interframe spacing. This extended interframe spacing explains normally after receiving the correct frame, a station would wait for the DIFS before transmitting again. But if a frame is received with error or corruption, the station instead waits for an extra interframe spacing, which is known as EIFS. As shown here, EIFS is calculated as SIFS plus acknowledgement transmission time plus DIFS. The purpose of this is longer waiting period to give the receiving station enough time to send the acknowledgement if it actually received the frame correctly, even if others detected it is as corrupted. This ensures synchronization and prevents unnecessary retransmission that could lead to further collisions. So if you see in the diagram, as we have seen earlier for the DCF operation, the source is waiting for the DIFS period. Again, if the station is free for the DIFS period, then it will transmit the RTS. And after receiving the RTS, the destination station will wait for the SIFS period, then transmit the clear to send. After receiving the clear to send, the source station wait for the SIFS period. So once the RTS is received by the another nodes which are all in the transmission range, immediately the network allocation vector will set and it will defer its time for transmission. And after hearing the CTS, the source will transmit its data. Once the data is successfully received by the destination, after waiting for the period of SIS, acknowledgement will be sent to the source and it will be received. And once this one cycle is completed, all the signals will wait for the DIFS period. Suppose if the receiving data is corrupted, instead of waiting for the DIFS period, all the remaining stations will wait for a extended interframe spacing. So which will allow the particular destination to decode its data, and if it is correct, it will again send the acknowledgement within the period of EIFS. Then the contention window will run, and according to that we can able to proceed further. To summarize, DCF relies on CSMA-CA with random backoff to manage the medium access. Acknowledgements ensure reliability of data frames. RTS-CTS reduces the collisions caused by the hidden stations. EIFS provides the additional recovery time in case of errors. Overall, the IEEE 802.11 map layer ensures efficient, reliable, and fair access to the shared wireless medium. Thank you all for your attention.